This video is for Chemistry in the Earth System, Unit 1.2, Thermochemistry. Today's essential question is, what determines whether a chemical or physical change absorbs or releases energy? And how can we measure and model those changes? Hello, baby birds! Let's begin our exploration of chemical energy and how it moves. This lesson focuses on the transfer of energy during chemical and physical changes, particularly in exothermic and endothermic reactions. Let's anchor our understanding with two real-world, culturally rooted examples. In Japan, during the summer festival season, fireworks known as Hanabi Taikai light up the sky. These fireworks are an example of exothermic reactions, meaning chemical processes that release tremendous amounts of heat and light energy into their surroundings. Meanwhile, in traditional ice cream making, which is pretty common in the US and parts of Europe, we add rock salt to ice to create freezing conditions. The resulting endothermic process absorbs energy from the surroundings, allowing cream to freeze into ice cream. Both of these examples represent opposite ends of the energy transfer spectrum, and they'll help us better understand the chemistry behind energy flow. So, this lesson will follow four major sections. First, we'll define and compare exothermic versus endothermic reactions. Then, we'll examine physical changes like freezing and boiling and how they also involve energy flow. Next, we'll investigate chemical energy transformations, including concepts like activation energy, Hess's law, and heats of formation. And lastly, we'll learn how to measure energy changes using calorimetry, understand specific heat, and apply all of this to real-life contexts. So let's begin with definitions. An exothermic reaction is a chemical reaction that releases energy, usually in the form of light or heat. This energy is released into the surroundings. In these reactions, the products have less chemical potential energy than the reactants. That energy difference is given off during the reaction. Some examples include combustion reactions, like burning wood, or fireworks, like we just mentioned. The synthesis of sodium metal and chlorine gas into table salt, which is NaCl, burning fuels like methane or propane, are all examples of exothermic reactions. So here's how it works. Chemical bonds store potential energy. When old bonds break and new ones form, energy is either absorbed or released. In exothermic reactions, the energy stored in the reactants is greater than in the products, and the excess energy is released, just like the bursts of heat and color in Japanese fireworks. Now for the endothermic reactions. These endothermic reactions absorb energy from their surroundings. In these cases, the products have more chemical potential energy than the reactants, because energy was added into the system. Some examples include photosynthesis, in which plants absorb sunlight to make glucose; melting ice, where energy from the air is absorbed to change phase; dissolving salt into water, like in an ice pack or when making ice cream. These are all endothermic reactions. Remember, if a reaction or process feels cold to the touch, it's likely endothermic, meaning energy is being absorbed from you or the environment. Now, chemical changes aren't the only ones involving energy. Physical changes, such as phase transitions, do too. Let's look at exothermic physical changes. First, freezing, which is liquid to solid. This is where water releases energy as it freezes. Then there's condensation, which is gas turning into liquid, like when water vapor condenses on a cold mirror. Then there's deposition, which is when a gas moves to a solid. Think of frost forming on a window. In all these cases, the system releases energy into the surroundings. Now, the endothermic physical changes. You'll notice that these are opposites. First, melting, the movement of solid into liquid. This is where ice absorbs energy to become liquid water. Then there's vaporization, when a liquid turns into a gas, like boiling water on the stove. And lastly, sublimation is when a solid turns to a gas. For example, dry ice turning into carbon dioxide gas. The key idea is this: if a process requires energy input, it's endothermic. If it's releasing energy, it's exothermic. And these principles apply to both chemical and physical changes. Now let's apply this idea to a real-world example: agriculture. Farmers sometimes spray water onto citrus trees like oranges during freezing weather. Now that might seem strange. Why add water in cold weather? Here's why. As the water freezes, right, because it's cold weather, it releases energy in the form of heat. The heat is leaving the water as it turns to ice. Remember, that's an exothermic physical change. That heat transfer of the energy leaving the water transfers that warmness to the surrounding air and protects the fruit from dropping below 0 degrees Celsius. A layer of ice that forms around the fruit also provides insulation. This is a perfect example of how understanding phase change and energy flow helps humans to use chemistry to solve real problems, like preventing crop loss during a frost. Phase diagrams also help us understand the conditions under which a substance changes between solid, liquid, and gas phases. This diagram map shows pressure on the x-axis against temperature, which is on the x-axis. And it shows regions for each state of matter. There are two special points to notice and remember. There's the triple point, which is represented by T, where solid, liquid, and gas coexist in perfect equilibrium. And then there's the critical point, C. Above this temperature and pressure, a gas can no longer be turned into a liquid, no matter how much pressure you apply. Phase diagrams show us how substances respond to changes in temperature and pressure and help predict phase transitions. So how do scientists measure energy transfer in a reaction or physical change? Well, like we've studied before, they use a process called calorimetry, which takes place in a device called a calorimeter. Remember, the basic idea is simple. A sample, say a hot metal, is placed into cool water. Heat flow from the hot object causes the cool one to heat up. The temperature change in the water is then measured. And from that temperature change in the water, we calculate the energy transferred using the following equation. Q is equal to mc delta T, as we've seen before, where Q is the heat energy transferred, measured in joules, C is the specific heat of the substance, M is the mass, typically in grams, and delta T is the change in temperature. Remember, because energy is gained by one substance, we can assume that it's being lost by the other substance. So when we have two equations of Q is equal to mc delta T, if we assume an isolated system, because that satisfies the law of conservation of energy, we can set those two equations equal to each other and solve for whatever term we need to. Specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Let's compare some. There's water, which has a specific heat of 4.186 joules per gram per degree Celsius. Again, we've mentioned this before, but notice that the unit mentioned on the screen in this specific case is joules per gram per degree Celsius, as opposed to kilogram. Whenever we're using grams in our calculation, we'll use the value 4.186. But if we add a kilo prefix to that, our value is now going to become 4,186. Now, water has a high specific heat, which means it heats slowly, but then retains the heat that it's gained. As opposed to aluminum coming in at 0.902 joules per gram per degree Celsius, which is on the medium side, which means it heats faster than water and is often used in cookware. Then there's copper, with a specific heat of 0.385 joules per gram per degree Celsius. This is a low value, which means it both heats up and cools quickly. But why does this matter? Think to yourself, on a beach, sand heats up faster than the water does because it has a lower specific heat. When you eat a pizza, the cheese stays hot longer than the crust because the cheese has a higher specific heat. Oceans keep coastal areas temperate, meaning kind of a medium temperature, due to the water's high specific heat capacity, which means it resists sudden changes. Even in an exothermic reaction, like burning magnesium or lighting a firework, the process doesn't start on its own. It needs a push. We call this push activation energy. Activation energy is the minimum energy required to start a reaction. Think of it like pushing a boulder over a hill. After you get over that hill, gravity, or in this case an energy release, takes over. For example, a sparkler, a small firework, needs a flame to start the reaction. For example, fireworks at the Hanabi Taikai don't go off until the fuse supplies the initial energy. Wood doesn't combust spontaneously. It needs an initial heat to overcome this activation energy. Now, if you reverse the reaction, the activation energy is much higher because now you're going from a low energy product to a high energy reactant, which requires more input. Hess's law says that energy change in a reaction is pathway independent. This means it doesn't matter how many steps the reaction takes. The total enthalpy change is the same. For example, if a reaction is too slow or complex to measure directly, break it into steps that you know. Do you need to reverse a reaction? Easy. Just flip the sign on the delta H, the enthalpy value. Do you need to multiply the reaction? Then multiply the delta H value accordingly. This helps chemists calculate enthalpy for reactions they can't observe directly. We can also use standard heats of formation, which is typically denoted as delta H sub F naught. Now, we can use this value to calculate a reaction's energy change. But let's go over our definition of standard heat of formation first. It's the energy needed to form 1 mole of a compound from its elements under standard conditions. And by the way, standard conditions means 25 degrees Celsius at 1 atmosphere of pressure. The heat of formation of any element, pure element by itself, in its standard state is 0. And that's going to be an important fact you want to remember. So we can use this formula. The delta H of the reaction is equal to the sum of the delta H of the products minus the sum of the delta H of all of the reactants. So let's tie everything together before we finish up. Exothermic reactions release energy. The products have lower energy than the reactants. Our examples being fireworks, freezing, or combustion. Endothermic reactions absorb energy. The products have higher energy than the reactants. Examples being making ice cream, photosynthesis, or boiling. Physical changes also involve energy transfer. Freezing and condensation are exothermic. Melting and vaporization are endothermic. Calorimetry measures heat transfer in systems using specific heat and temperature change. Activation energy is the energy needed to get any reaction started. And Hess's law and standard heats of formation are tools used to calculate energy change for complex or indirect reactions. Understanding thermochemistry not only helps us in labs, it also helps explain real-world events like why fireworks explode, why cheese stays hot, how crops survive frost, and how ice cream freezes. At this point, you should be able to generate a full and appropriate response to today's essential question. What determines whether a chemical or a physical change absorbs or releases energy? And how can we measure and model these changes?